Sabine Hossenfelder created a video titled Physicists Find Missing Link Between Quantum Mechanics and Gravity. In this video, she reviews a recent paper that suggests quantum fluctuations of spacetime might influence the motion of stars and galaxies. It's an intriguing idea, and the authors highlight something important. Because general relativity is nonlinear, the average of a product isn't the same as the product of averages. That means quantum fluctuations don't simply cancel out. They can feed back into the motion of matter. But the paper stops at a crucial point. To use their equations, you need a model of what those spacetime fluctuations actually are. And that's the part they don't provide. Today I want to explore what that missing microphysics could look like, not as a replacement for the paper, but as a concrete example of the kind of structure their framework requires. What the paper actually shows. General relativity contains nonlinear terms, products of the metric and its derivatives. If the metric fluctuates quantum mechanically, then those products don't average the way classical intuition suggests. The authors argue the following. Locally, the effect is tiny. But on galactic scales, the cosmological constant amplifies it, potentially leading to observable deviations from standard gravity. It's a clever and mathematically consistent idea. But it depends on something the paper doesn't specify. What is the quantum state of spacetime? Without that, the framework is incomplete. The gap Sabine highlighted. Sabine's critique is straightforward. The paper is formally correct. But it doesn't quantify the effect. And it doesn't provide the underlying physics of the fluctuations. So the clear difference claimed in the press release isn't demonstrated. In other words, the formalism is waiting for a physical model. This is where a mechanical perspective can help. A mechanical example, the vacuum energy substrate. Imagine spacetime is not just geometry, but the large-scale behavior of a physical medium, a substrate with stiffness, density, and excitations. In this picture, dark energy corresponds to the large-scale compression state of the substrate. Inertia arises from how objects interact with that medium. Gravity is the mechanical response to displacement loads. Mass is a localized deformation created by energy binding. This is the vacuum energy substrate, or VES, a mechanical model that treats spacetime as a medium rather than a purely geometric object. The point here is not that VES is the answer, but that it provides a concrete example of the kind of microphysical structure the paper's equations require. How a substrate model fills the missing pieces. First, the paper finds that quantum corrections scale with the cosmological constant. In a substrate picture, the cosmological constant reflects the compression state of the medium. Compression changes stiffness, and stiffness changes how fluctuations propagate. So the scaling emerges naturally. Second, the paper suggests quantum corrections are negligible locally but may matter in galaxies. In a substrate model, local behavior is dominated by mass loading, while large-scale behavior is dominated by the medium's stiffness and compression. This mirrors the transition seen in galactic rotation curves. Third, the paper needs a model of spacetime fluctuations. A substrate provides one. Fluctuations are mechanical excitations of the medium, not abstract metric wiggles. Fourth, the paper hints at a connection between quantum behavior and modified gravity. In a substrate model, both arise from the same underlying medium, so the connection is structural rather than coincidental. Why this matters? If quantum gravity ever produces observable effects on galactic scales, it will require a model of spacetime that includes microphysics, something beyond the smooth metric of general relativity. The paper Sabine discussed is a step toward connecting quantum structure to large-scale dynamics. A mechanical substrate model is another step, one that provides the kind of physical fluctuations their framework needs. This isn't a claim of a finished theory. It's an example of how microphysics could supply the missing input. Thanks for watching.